Okay, so let's begin Chapter 3, which is called Logic, and Section 3.1 is called Logic Statements and Their Negations. Before I get into 3.1, though, I want to talk a little bit about why we're going to learn logic, or what this chapter is going to cover. So, what we're going to cover in this chapter is logic statements themselves, so statements that have some truth value that can be assigned to them. So statements that can be considered as true or false. And then, so we're going to spend a lot of time talking about truth values. We'll look at these things called truth tables that let you figure out the truth values of very long logical statements. And it'll sort of culminate in section 3.4 with these logic statements being put together in such a way that they could be considered as arguments. And we'll learn the difference in different types of arguments, different fallacies, false arguments, and the difference between inductive and deductive reasoning. So the first definition, or the first item, is a definition in this section. If you're following along in the notes, you'll see that it's a mathematical statement. So a mathematical statement is a phrase that can be assigned a truth value of true or false. Okay, simple enough, is a phrase so we say a truth value just being one of two things, true or false. But not both at the same time. So a mathematical statement can be either true or false, but not both. So if you've ever done one of those experiments in elementary school where you've got to do, you're learning about the scientific method and you've got to construct a hypothesis, then you'll remember that a hypothesis should be something that can be assigned a truth value of true or false, right? You need your hypothesis to be falsifiable. That's a fancy way of saying it. It can't be an opinion. It can't be an opinion. It has to be a mathematical statement. So we can already see how if mathematical statements is the very first definition in this logic chapter, and mathematical statements are like the backbone of the scientific method, then surely logic must be a very important aspect of mathematics, and beyond mathematics, just in science in general, just in everyday life, really. Okay. So let's do some examples of things that are not mathematical statements and things that are mathematical statements. So, for example, say example of a non-mathematical statement. I may say logical statement instead of mathematical statement later. Kind of interchangeable there. Example of a non-mathematical statement might be something like, well, one of the examples I give in the notes is, this is the best movie ever made. So how about instead of this is, let's just say, what's a movie that has a short name so I don't have to, how about The Matrix is the best movie ever made. Okay, this is a non-mathematical statement because it's an opinion. It's subjective. It's subjective. We cannot assign a true or false value to this because not everyone would agree. Right? So I'd probably say false because I could probably think of movies that are better. I mean, it's good, but I don't know if I'd say it's the best, but other people might say it's true. So this is not a good mathematical statement. It's an opinion, right? So here's an example of how we could twist this statement so that it could be a mathematical statement. What if I said the matrix received the highest Rotten Tomato rating? So Rotten Tomato is a rating scale for movies. In the year, when did The Matrix come out? In the 90s? I don't remember. I'm just going to make something up. 1995. I think it... No, did it come out in the 2000s? Well, anyways, who cares? Replace The Matrix with whatever movie you want there, and the time frame with whatever makes sense to you. I don't even know if Rotten Tomatoes was a thing in 95. Probably not. But, let's say it did. Then this is something that is a falsifiable statement, right? This can be proven true or false because we can go do research for the specific year, find all the ratings, and see if it received the highest one. This is something that could be proven to be true or false. So it is a mathematical statement. As another example, more examples. Let's say, what if I said this paper that I'm writing on is white? Well, at first you might say, yeah, I mean, it looks white, so the paper is white. But what if I was to compare it to something else that we would all consider to be white and it looks a slightly different color? So I would say this is kind of a gray area, but if we want it to be super technical, and this is math class, and the whole purpose of these logic statements is to provide this structure of like rigor and technicalities that can be taken into other areas. So let's be rigorous and technical and say, no, this is not a mathematical statement because it's kind of ambiguous. Like, what does white mean? You know, like, I'm white, right? So I could say my arm is white, but clearly these are different colors, right? So what if I said this paper, when scanned by a computer, will yield, how does it go? Okay, will yield the color known as white with hexadecimal format or code hashtag FFFFF. Wait, 1, 2, 3, one more F. So, if you know, if you've ever done any coloring or illustration or graphic design with computers, then you know a computer assigns to each color some code that's in, this is called hexadecimal format or hexadecimal code. If you've taken any computer science classes, you've learned that there are different number systems. Like we use the we use the decimal number system, 0 through 9. Then there's the binary system, which is just 0 and 1, and then there's hexadecimal, which uses 0 through 9 and the letters A through F. So this is something that is much more complex and technical, but we could potentially take this paper, get it scanned by some kind of computer with the appropriate software, and get a color code back. And we could say, if the computer says that it's this code, then we would say this statement is true. And if it's anything else, we would say the statement is false. So I would say that is a mathematical statement. Okay, Okay, let's talk about paradoxes real quick. We're not going to work with paradoxes. A paradox is just a statement that contradicts itself, so I'll just say a statement that contradicts itself. They're fun, but we're not going to use them because obviously, contradicts itself. If we've got a statement that contradicts itself, then it cannot have a truth value of true or false because it's just looping. It's like a circular argument. It's never going to be true or false, so we're never going to use them. Just want to point them out. Just kind of say what they are. Give an example. I give 3 different examples in my notes. My favorite is, or the one that's easiest to understand to me, is I lie all of the time. All of the time. To me, that one's just the easiest to understand, to see why it's a circular argument. Because obviously if I lie all of the time, then this statement itself is a lie, and then you could just keep spinning back and forth. It contradicts itself, right? So it's a paradoxical statement. So these are not mathematical statements, because it cannot be assigned a true or false value. Okay. Okay, so from now on, we're just going to be working with mathematical statements. We defined it, we talked about what things could be mathematical statements and what things could not be. And from now on, we're just going to be working with the mathematical statements because anything else is not useful to us in this setting. So, the negation, here comes the next definition, the negation of a logical statement or a mathematical statement is the logical opposite of the mathematical statement, of that mathematical statement, so the original. That's the negation. Okay, so negations are pretty fun to work with, and they're going to be super important. Oh, I should also say, negations have the opposite truth value of the original statement. Okay. So if a statement is true, its negation is false, etc. Okay. Easy enough, right? And for some examples, it really is that easy. So let's see. Example 1 from the, well, let me go ahead and enumerate it the same way. I call it example 1, following along with the notes. Given each statement, provide the negation. I'll just say provide each negation. Okay, part A says that 5 is a prime number. Five is a prime number. Okay, so the negation, this is how we're going to denote this. Oh. Okay, so in the notes I named this statement with the letter A. So we can do that. We can name statements with variable names. So it's a little confusing, but for part A of example 1, this statement I'm going to call A. You could call it X if you want, if you're confused, because, 2 A's here. So this statement, A, is 5 is a prime number. And what I want for the negation is this, the negation of A. So this symbol means negation. And in the notes, I use this symbol because for whatever reason, the program that I use to code up the notes doesn't like the little tilde symbol. So this or this means negation. So we're going to be using symbols or letters a lot in this chapter to represent statements. So here I want the negation of A, and it really is as easy as saying 5 is not a prime number. Now, let's go a little bit further and say what the truth value of each one is. The truth value of the statement A is true, right? Because 5 is a prime number. The truth value of the negation of A is false, which fits to our definition, which says that negations should have the opposite truth value of the original statement. And the negation of A is false because it says 5 is not a prime number, but that's false because we know 5 is a prime number. Okay, so simple enough, simple enough. Now for part B, I've named the statement, the door is, well, I've named the statement B, and the statement is, the door is not closed. So the negation of B then is going to be the door is open, or no, is not open, we could say, but we'll just say is open. Or we could say not closed, but really a door is either open or closed, right? It's binary. It's either 0 or 1. It's either open or closed. Just like back here with example A, a number is either prime or it's not, right? It's either prime or it's not. A door is either open or closed. So far, pretty simple, right? And the truth values of each of these would just depend on what door you're talking about. But it still can be a mathematical statement. We would just need to know what door, right? Okay, so let's talk about an example that's not either open or closed or prime or not. So for part C, naming the statement, the letter C, none of the tourists brought raincoats. None of the tourists brought raincoats. Okay, and we want the negation of C. Okay, what is the logical opposite of this statement? So imagine a group of tourists in front of you, just like 5 people, and it's raining, and none of them have raincoats. Okay. What would be the logical opposite of this statement? So you're going to be tempted to say all of the tourists brought raincoats. But this is a situation where there's a quantifier here specifying that none of the tourists have raincoats. And we need to be really careful about negating things like that where they're talking about some quantity of things. So back here with example B, there is no quantity, right? There's one door and it's either open or closed. But here, there's like a gray area where you could have one of the tourists having a raincoat, all of them, at least one, 0, so there's many options. So the way we have the logical opposite of the statement that says none, we say if none of the tourists brought raincoats, the logical opposite would be at least one of the tourists brought a raincoat. Now they actually work this same problem in the textbook, and their answer is that some of the tourists brought a raincoat. And that says the same thing. Some just means at least one. At least one of them did. So if you saw all the tourists in front of you and none of them brought a raincoat, then this statement would be true and this one would be false. Okay. I'm going to make another example deviating from the notes a little bit here. So this example might help you picture this relationship a little better, because I'll literally give you a picture for it. So let's say statement D, the number x is greater than 5. The number x is greater than 5. Okay, so I could really just rewrite D as x is greater than 5. Okay. So this is just saying the same exact thing that I said here. The number x is greater than 5. So if I drew this on a number line, here's 0, here's, let's put 5 over here. So x, is greater than 5. So if you remember, I had a graph inequalities. I'm putting an open dot over 5 because x cannot be equal to 5. X can be 5.00001, but it cannot be equal to 5. And of course, every number out here is greater than 5. So what is the logical opposite to this statement? So there are lots of numbers that are bigger than 5, right? Like 6 and like 10,000, right? Infinitely many numbers that are bigger than 5. So would it be appropriate then to just say the number x, for my negation, the number x is equal to 0, because that number is less than 5? But that's not fully complete and correct, because there are many numbers that are the opposite of being bigger than 5. There is 0, there's 4, there's all the negative numbers, there's fractional numbers in here, right? There's infinitely many. So the negation, your negation should be complete, right? It can't just be true for one piece of the data, right? Just like back here with saying none of the tourists brought raincoats, the logical opposite, if we said all of them brought raincoats, that's not true. It would be a part of the logical negation, but what about the case when 2 of them have raincoats and 3 of them don't? Then that's, so you've got to consider all the possibilities. So the way I could negate this statement, x being greater than 5, I could say the number, in order to get all the numbers that are going to be the opposite of being bigger than 5, is less than 5, but not just that, less than or equal to 5. Because I want to get every single number that could be the opposite of this statement. So I'm going to say x is less than or equal to 5. So that's going to catch all these numbers, including 5 itself, that are the opposite of being bigger than 5. Okay. So in order to have a legitimate negation for statements like example C or D here, you've got to catch every single part of the negation. You can't leave any situations out. It's tricky, but it just takes practice. I just realized back here I meant to say in example B, closed. Sorry if that was driving you crazy, probably was. If the door is not closed, that means the door is open, so the logical opposite of that is closed. Sorry. Alright. Alright. Let's talk about compound statements. Whenever I say statement now, I'm referring to a mathematical statement. So this is a compound mathematical statement. Is composed of 2 or more statements, mathematical statements, connected with or joined together joined together with connective words such as and, or implies, which can also be written as an if-then statement. Okay. Each of these has a corresponding symbol. The symbol for and is like an upside down capital V. The symbol for or is like a capital V. And the symbol for implies is an arrow with 2 lines. Okay, so we can connect 2 simpler statements with each of these words. So I could say, they don't even have to be related. I could say 5 is a prime number and none of the tourists brought raincoats, right? So if I wanted to say that, based off of from example 1, we can say 5 is a prime number and none of the tourists brought raincoats. We can say this as, or more simply, as 5 is a prime number. We use the letter A to denote that statement. And then there's the word and connecting the statements. And then none of the tourists brought raincoats. We called that the letter C. So there we go. So you can see how naming the statements with variables and letting each of these connective words have a little symbol to them makes writing statements, compound statements in particular, much simpler, much easier to write down. So the and is right there. Let's do some more examples. So this is example 2 from the notes. Using the simple statements below and logic symbols, write the compound statements. Using symbols, just shorthanding the instructions there. So part A, or well, rather before I write these parts, I gotta name each of these statements. So we're gonna name the first one P, which is it is raining. And the second one is Q. P and Q are traditionally the first symbols, or rather variable names that we use for mathematical statements. Q is it is sunny outside. Now, for this example, I'm not concerned with the truth value of the statement, okay? Because the truth value of these statements would depend on where we are and what time of day and, whether it's raining or not, whether it's sunny or not. So we're not concerned with the truth value. Part A says it is sunny outside and it is not raining. So again, not concerned with the truth value. We're just wanting to practice writing down statements with their corresponding variable names and symbols. Okay, so I can almost go like literally piece by piece here. It is sunny outside, that's Q. The word and, that's this symbol. It is not raining. Well, P is it is raining, but this is it is not raining, so this must be not P. There we go. So this is read as, if you want to read these symbols without worrying about what they mean, it's read as Q and not P. So you can almost go literally piece by piece. The only thing is with grammar, we don't say, it is sunny outside and not it is raining, right? So, that's not grammatically correct. So when you put it in English, you've got to move that word not somewhere where it makes sense grammatically. But when we read it as symbols, we read it left to right, Q and not P. All right. So part B says, if it is raining, then it is sunny outside. Again, not concerned with the truth value. This would depend on where we are, right? So, an if-then statement is going to be the arrow symbol. So this statement could also be written as, it is raining implies that it is sunny outside. That's a little weird though. So it's written as an if-then statement. So the way we would do this one is we would say, okay, the first statement is it is raining, so that's P. Then we would put the symbol for if-then in between the letters, like this. And then it is sunny outside, that's straight up Q. There we go. So this could be read as, with the symbols, P implies Q, or if P, then Q. So if you read it as an if-then statement, then you can't really go, as nicely left to right as we did with these. Like, you've got to pull the statement out from the if, pull the statement out from the then, and put the if-then symbol in between the two statements. Now, if I wrote it as an implies statement, then it would be much more lined up, like a one-to-one relationship there with the statement, variable names, and the symbols. Okay. Part C says, similar thing, if it is raining, then it is not sunny outside. I'm going to squeeze it in there. Boop, boop. Okay, if it is raining, then it is not sunny outside. So, again, this is an if-then statement, so my symbol in between is going to be that implication arrow. The first statement is still P, it is raining, and then not sunny outside, so this would be not Q. And we would read this as P implies not Q, or if P, then not Q. Alright, the last one. Now this is a weird one. It is not the case that it is raining or it is sunny outside. Okay. So how would we write this? It is not the case that that statement is saying we want the logical opposite of the rest of the statement out here. So it is not the case that it is raining or it is sunny outside. So that means we're going to start off with a negation here. And we're going to negate this entire statement. So the rest of the statement, ignoring this little mess up here, the rest of the statement, it is raining or it is sunny outside, is going to get negated. So it is raining is P, it is sunny outside is Q, and the or symbol is that letter V, the opposite of the and, right? So it is raining or it is sunny outside, that's going to be P or Q. But I want to negate this entire statement, the entire compound statement here at the back. So I use parentheses, I use those grouping symbols from algebra to say it is not the case that, and then the whole rest of the statement. So this is read as not P or Q, which is very different than just saying not P or Q, right? So incorrect answers here would be something like this. This would be incorrect, whereas this would be correct. So grouping symbols make a difference here. They make a big difference. Let's do a little exercise in logic here and think about what this is saying. So we're not really going to get into the truth values of this at all, or what I'm about to have you try is something that we're actually going to work on in a later section in this chapter, but I think it's a good exercise now anyways. What is this saying? Like, what would be a simpler way to say it is not the case that this or this is happening? Because who talks like this, right? Who really talks like this? No one, unless they're trying to be annoying, right? So we'll just start with it is raining or it is sunny outside. Okay, so that means this statement would be true as long as one of those two things is happening. Because as we'll find later, that's how an or statement works. It's true as long as one or the other or both is true. So if I look outside and it's raining and it's dark, then that part of the statement would be true, because one part of it is satisfied. If I look outside and it's not raining but it's sunny, then this part is satisfied, the statement is still true. The only time it wouldn't be true is if both of these are false. So if I look outside and it's not raining and it's nighttime, so it's dark outside, then this statement would be false. That's the only time it's going to be false. And in fact, isn't that what a negation wants, right? It's the logical opposite of P or Q, this statement, it is raining or it is sunny outside. So this is equivalent to, is the same as saying, it's the same as saying it's not raining and it's dark outside, or rather, it's not sunny. So it's the same as saying it's not raining and it's dark outside, or it's not raining and it's not sunny outside. And this is actually a theorem that we're going to talk about more in section 3. I think it's 3.3, I don't remember. But anyways, it's a good little exercise to think about that, how this and this could be logically equivalent to each other. Okay. So example 3 is just more of this practice using logic symbols. I've just given more variables here, so A, B, and C, 3 different statements. I'm not going to work it out because I think that you can figure it out. The statements are not much more complicated than what we did in example 2. So I'm going to skip to example 4, which is kind of going the opposite direction. And it says, write the symbolic statement, the negation of B, so not B or A, in words by using the given simple statements. So the word A, or the statement A, is my umbrella broke. And B is it's raining outside. Okay, so if I wanted to write this statement, not B or A, so the key is knowing what these symbols mean, right? So you can make some little flashcards. It's not real hard to remember. There's only a few of them, right? The way I remembered in the beginning is that this is associated with and and it kind of looks like a capital A, so that's how I associated it with and. And as long as you get that one, these are the only two you could ever, to me, mix up. So if you can just remember that this one is and, then the other one, by process of elimination, must be or. So I want to write not B or A. That's going to be the same as it is not raining outside. Or, there's the or, my umbrella broke. So we're not worried about if these statements make sense, or if anyone would talk like this in the real world, or what the truth value of this statement might be. That's going to come in the next section, where we're actually going to start looking at truth values, and we're going to look at all the different possible combinations of truth values given multiple statements. So each statement has two possibilities, right? My umbrella broke can either be true or false, and this statement can either be true or false. So when I put them together, how many combinations do you think there are going to be? How many possible combinations? And how would the and, or, and imply symbol affect those combinations? That's what we're going to talk about in the next section. So make sure you note those problems I gave for review. Just add them to the big set of problems, and you can use those problems as a review before the exam. Looks like I gave quite a few from this section, but this section's really not that heavy. It's just kind of an introduction, learn these symbols, understand kind of those weird negations where you've got multiple situations going on, especially example 1C and example 1D. Okay, that's it.